Hi and hello. In this video, what we will see is a review of probability theory that is needed for understanding the course. So, this is does not going to give you this material that you are going to cover, does not going to give you the complete picture, but at least you will get familiarized with the notations that we will be using in the rest of the course, and also like what are the concepts that are most important to us. Okay, so that will be clear from seeing this. Okay. As you know, like every stochastic model is specified in terms of what is known as a probability space. Whether you say this explicitly or not, like there is always an underlying probability space. So, what do we mean by that? A probability space is nothing but, we have written down here, first a sample space, which is nothing but the collection of all possible outcomes of a random experiment. And the next thing is a bit more technical, which is we call it as an event space, but technically it is called as a sigma field or a sigma algebra, which is basically a collection of events. So, one should naturally include whatever possible events that you can think with respect to the random experiment inside this set. So, a non-empty collection, whatever is the condition is what is given here. Okay. The third ingredient for this is a set function, which is a P, which is a mapping from F to R, which is what we call it as a probability measure or a probability function or simply a probability, and that satisfies these three properties. First is the non-negativity property, the second is the total probabilities must be equal to 1, and if you have a sequence of disjoint events, disjoint means EI intersection EJ is empty set, then probability of their union is sum of this probability. This is known as a countable additivity property. Okay. So, any set function that satisfies this property will be called a probability. So, these three ingredients together, put it in a triplet form, is what is known as a probability space, right. So, every stochastic model is specified in terms of the underlying object of this probability space. Now, as a simple example, if you look at, so if you can look at the tossing of two coins, so the sample space would be this, as you all know, and you can take any event space satisfying the condition that is given above. So, we take this to be our F, which is normally is taken in case omega is finite or countable, which is nothing but the power set of omega, which means set of all possible subsets of this particular set omega is what is called the power set. And you can define probability on what we call these 4 elements, which are all elementary events in this omega. So, if you define probabilities of these 4 such that they sum to 1, and for any other event in F, if you define in this manner, so then you will be defining a probability. So, this is a simple example. Of course, the specification of this sigma field is what is important here, and on top of it. So, if you change F, then you will also change P, or even if you keep F, you can define P in different ways. So, you get different probability spaces. So, there is always a probability space in under every stochastic model. Okay. Related to that is the concepts of what we call, what you know already as conditional probability and theorem of total probability and Bayes theorem. So, this is these are all elementary stuff that you can recall, like what we mean by a conditional probability. The total probability is one of the important result, right. The theorem of total probability is one of the important result which helps us to compute probabilities of certain event very nicely. Say what you have is this particular results that we are pointing out here, that if you have a mutually exclusive and exhaustive events such that each of these probability is strictly greater than 0, then you can compute the probability of this any particular event A by conditioning on A intersection with EIs, okay, and then summing over each of this is what is given here. It is a very important concept which is being used while you want to compute probability of certain events, right. You can break it up into smaller pieces and then you aggregate together, that is what it would mean. Bayes theorem, of course, you will also know, you can recall from even from the elementary stuff. Okay. Related concept is what we call as independence, right. This is here we are defining independence in terms of probability. So, sometimes it is also called stochastically independent or statistically independent, no matter whatever it is, the definition is this. If you have two events, say probability of, you would have seen in terms of this, right, E intersection F is probability of E into probability of F for 2 events. So, what we have given here is a finite number of events and any finite sub collection of those, and then we can extend that to countable and also conditionally independent, what we mean. Okay. So, if probability of this event is given as product of probabilities of the individual ones, then we say these two are independent. Okay. That is what we mean here. Okay. So, this is the basic probability idea, but on what generally people work on is something which you define on a probability space, which you use further in all your modeling purposes. Okay. A quantity of such interest is what we call this random variables, right. So, what is a random variable here? That you have a probability space and a function, a real valued function on omega is called a random variable if inverse images of these sets are all inside this F for all A in real number, right. So, this is technical, which is required. Suppose if omega is uncountable, then this makes much more sense, but whenever omega is finite or countable and F you take it to be the power set of that particular set omega, then any real valued function would satisfy this. Okay. So, but otherwise for other cases, whenever your F is not the power set of this omega, then you need to specify or check this condition for this function to be a random variable. So, what it does is that is what is given here. The random variable x is used to push forward the measure p, which we defined on omega f p, to a measure on r, which is what is called the probability distribution. Okay. That probability distribution, so it is also giving another probability space only, but you are defining it on R and a sigma field or an event on R, event space on R and associated probability measure, right. That is what this random variable does. The purpose is that to make our life easier. Okay. You would have seen in the basic probability examples in basic course that the reason why you define a random variable and so on. So, that probability measure is typically defined in terms of what we call as a distribution function, which is defined to be this, right. This you all know that f of x of x is probability of x less than or equal to x, which is nothing but this quantity, probability of this measure. So, in order that you can assign probability to this is the reason why we want this to be inside this f, the event space. Okay. And you can recall what are the properties of this distribution function and so on. So, random variable in our sense is just a function that does not depend on the probability p, but the distribution of the random variable depends on probability p. So, for most realistic purposes, a stochastic model or a probabilistic model is defined in terms of random variable and its distributions, right. Random variable means the values that the particular random variable can take and the associated probability measure. But how it comes? It comes from the basic construct of the probability space. There you define x, that gives rise to this. So, basically what one can see is that this x along with this fx, this fx can be defined in equivalently many different ways, right. Then be called as a stochastic model or a probabilistic model. Of course, from the same probability space you could have multiple random variables defined, like in our queuing situations, like there could be an intra-arrival time, there could be a service time, like there are two random quantities that you need to define in order to define a complete model, right. But all these things have an underlying probability space, that is what you need to remember. Okay. Now, as I said that fx can be represented in many different ways. One of the ways which is very simple is this particular case of the discrete random variable case, right. What do we mean by a discrete random variable? A random variable is said to be a discrete distribution if there exists an at most countable set Sx, which we call support for the random variable x, such that there is a mass at each of these points and the total mass is equal to 1. Okay. So, such Px, that function Px is what is called the probability mass function, as you know, and the relationship between fx and px is given through this representation and px and fx in the reverse way. So, as a whole, like this line gives you the representation from or the relationship between fx and px here. Okay. As opposed to this, another class which is also very commonly occurring is continuous random variable. So, a random variable is to have continuous distribution if there exists a non-negative integrable function, say f of x, such that your capital F of x can be written in terms of this. So, this particular f of fx is what is called the PDF of the random variable. So, this Sx will be the support. So, you can represent. So, basically then random variable instead of distribution function, if the random variable is discrete, then random variable and its probability mass function, and if the random variable is continuous, the random variable and its the corresponding PDF function would define the model, like the so called whatever we could call as a model for it, right. So, you can again recall certain properties of this PMF PDF, which is what you can recall, okay. And some of the common examples that we might encounter or you would have encountered are these distributions. For example, this binomial distribution, geometric distribution, Poisson distribution, these are all forms under the class of discrete distributions. So, there is exponential distribution, uniform distribution, normal distribution and say gamma distribution, these are all in the continuous distributions, of which the most relevant, if we are doing the discrete time analysis, then you will be requiring this discrete time distribution of geometric, and of course, Poisson distribution also would occur even in continuous time, and in continuous time when mostly we will be concerned with exponential and gamma distribution when as the most important distribution that is we would require, and Poisson distribution also would arise naturally in between. So, some of the well known distributions you can recall and correspondingly like what is the. So, this is the notation, like whenever we write in this form, this is just the notation that we are going to use in order to represent such distributions is what you can understand here. Okay. Now, once we have these distributions in mind, there are always certain quantities associated with the distribution which is of importance. In suppose if I want to know the complete picture of the random variable x, then I need to know the distribution function equivalently either PMF or PDF. If I do not know that completely, then it does not mean that I cannot say anything about the random variable x, right. But you can say something if you know some more or some other quantities other than this, but if I know the distribution function, I can answer any question that is related to the random variable, that is what it would mean. But there are certain quantities in that sense would be of importance or interest whenever you are dealing with any random variable, even if you have distribution function, but you want to again summarize certain informations in a very compact form. So, quantities that are used to do that business, and also it will help us in the analysis part as well, are certain quantities which are called expectations. Okay. Suppose if I have a discrete random variable with a probability mass function Px and support Sx, then we say expectation or simply mean of x is defined by this quantity provided this sum is absolutely summable, right. That means this, the absolute summability, as you know, we require it so that this is defined in a meaningful way. Okay. Similarly, in a continuous random variable with a PDF fx, the expectation is defined to be this provided this is finite. Okay. Now, both this form, right, expectation here we are writing it in terms of sum, here we are writing it in terms of integral, can be written using Stieltje integral. For those of you who are not familiar with Stieltje integral, it does not matter much, but it means this notation is what is then will be used. So, what does this mean? In discrete case it would mean this sum, and in continuous case this would mean this sum, that is all. Okay. Of course, if you know the theory about Stieltje integral, it will be convenient, but otherwise you do not need to too much on this part. Okay. So, this is and also like random variable, there are mixtures, what we call mixtures, meaning that it has a continuous part, it has a discrete part, both of them are available as in a single random variable case. So, that is what you call mixtures, or not mixtures really, mixed random variable, or mixtures means like it is in certain proportions you are mixing the different distributions and so on. Okay. For all those things you can write in a similar way, right. And also if x is a random variable and g of x is a function of this random variable where g is some nice function, we will assume that some continuous function or some increasing function and things like that. So, this is a technical term you need to introduce, we will not do that. So, this is some nice function. Then this its expectation can be computed, right, in this manner. This is an important result, because otherwise what would require? You would require a function of g and then which is we call y, obtain its distribution function y and apply this definition. But rather you can directly apply this. For example, expectation of g of x in discrete case would be summation of g of x px. That is how it will look like when you write it in this form in this case. Okay. And again you can recall the properties of this expectation operator. This is an operator, whether it is linear and so on, like, so that you can do certain operations, right. Expectation of x plus y, you can write it as expectation of x plus expectation of y. So, the relevance for us is that you can break it up. If you want to compute expectation of certain quantity, you can break it up into pieces and then you can compute individually and you can sum it up, right. That is what it would mean. So, what does it mean for us? All those properties is fine, but what is its significance? What does it mean for us is what is more important for us. Okay. Now, there are certain special expectations, like so expectation of x to the power r. If you take the g function to be x to the power r, then this is called the raw moment of x, and the first one mu1 is what is we called as mean mu. Most often we will simply denote it as by mu rather than mu1. Similarly, mu r dash, which is this quantity, is called the rth central moment. We are assuming that all this expectation exists, that is what it would mean. And then mu2 dash is called the variance, which is simply we will denote it by sigma squared or variance of x is what. One quantity which is of use in our studies, which is dimensionless to make, is this coefficient of variation that talks about how variable is a random variable compared to another random variable, is given by this coefficient, which is called as the coefficient of variation, which is nothing but the ratio of the standard deviation of x divided by mu. Okay. Some other expectations which is again useful in our when we do the analysis of the models is this what we call moment generating function or simply MGF, which is defined to be this particular expectation provided the expectation exists in some neighborhood of the origin, right, in some interval around origin, this expectation should exist for t in some interval around origin. Okay. So, if it exists, then the derivative of all order exists and its raw moments can be obtained through this relationship for all positive integers k. And whenever this MGF does not exist, of course, as you know that the MGF need not exist for every random variable, then people have to work on based upon the characteristic function which is always exists, which is defined to be expectation of e to the power itx, right. So, that always exists, but this is more complex to work, but whenever MGF exists, we will be working with only MGFs here. Okay. Another generating function or which is relevant to our case when we have a non-negative integer valued random variables, or what is called is probability generating function, which is defined to be this particular expectation, which is nothing but this expression, right. So, essentially it means that the coefficient of z to the power n will give you the corresponding probability. So, that is why it is called probability generating function is what then you call this one. Okay. Now, as opposed to univariate case, now you could also have a scenario where on the same probability space, which means that describe your original model, you could define multiple random variables, right. So, for example, if you want to define a population's certain characteristics, like for example, height and weight. So, height could be one random variable, weight could be one random variable, right. So, that is what when you have, then you have relationship between, obviously as you know height and weights are related. So, there will be some relationship will be there, or there is no relationship will be there, all those things will be studied through what we call jointly distributed random variables. So, which is defined to be through a random vector what we call, or a multi-dimensional or a multivariate random variable, or simply a random vector, right, which is nothing but this quantity x, where each of these are random variables on the same probability space as each other, which is the same probability space is what we are looking at it here. Okay. Now, just like for a univariate random variable, we have defined a probability function, either distribution function or PMF or PDF equivalently. Here also for any random vector, you have what we call joint distribution function, which is defined to be this, which is just an extension from one dimensional to n dimensional as you see here. Now, from this one can obtain what we call as marginal distribution functions in this, which are defined in this manner for suppose if it is 2 random variables is what you are considering and you are looking at the marginal distributions of x and y, then this is how you can obtain them. And you can now then recall certain properties of this joint distribution functions and so on. Okay. Again, in a random vector case, we say that this random vector is discrete if again there is a countable set on which this jointly xy and this xy, the number of sets, number of points the xy in R2 in this particular case, if this is countable and you have this probabilistically greater than 0 for all those points such that total sum is 1. Then you say this one is a discrete distribution, this random vector is a discrete random variable, a random vector in this case, particular case. Okay. And then you can define just like a univariate case, joint PMF is, which is basically representing this quantity here, and from which you can get the marginal PMF. Okay. Another case as usual is continuous case, when you say that random vector xy is of continuous type, if again there exists a function in R2 such that this relationship satisfies, then we call this fxy as the joint PDF of xy, and right. So, again you can recall certain properties and when you will call and everything, and not just that, again in a similar way what is the meaning and definition of expectation of g of the random vector x, right, which is similar way one can define it here. Okay. And when you, as I said, when you have more than one random variable on the table, you have the question whether they are related to each other or what is their relationship in a way. Okay. So, one needs to study about these random variables being independent or not. So, how do we define the notion of independence in case of random variable is again in terms of distribution function. So, the joint distribution function is can be written as product of the marginal distribution functions, then we say these random variables are independent. Okay. So, again this condition can be written down in a simpler way whenever, right, equivalently whenever you have either PMF or PDF exist. Whenever that is not the case, as you know in elementary probability theory that a PDF, for example, for every distribution function that need not be corresponding to PDF. So, in such cases like one can not write, one has to use this definition, but whenever these exist you can write down this in terms of the PMF or PDF. This is for easy understanding. Okay. We will be using mostly in that form only. And similarly, when two random variables are independent and g and h again are some nice functions, right. So, then the expectation of this quantity is can be written in this form. We are assuming that all the expectations would exist. Okay. With respect to two random variables, then we have certain quantities apart from mean and variance that we define even for univariate distribution. Of course, even in this case for each random variable you have mean and variance, but then you also have what we call covariance, which is defined to be this particular expectation, which is given to be this expression, and equivalently the correlation coefficient, which is defined to be this. And you know what are the relevance and what is the define, what are the properties of all these notions, random vector, variances, covariances, correlation coefficients, with and without independent, what will happen and so on. If you have, so whenever this rho is, as you know, this modulus of rho is less than or equal to 1, which means rho lies between -1 and 1, both ends included. When rho is equal to 0, we say that the two random variables are uncorrelated, but then that does not imply in general that the random variables are independent, but in certain cases it might imply under what condition and so on. So, these are what we say with and without independent notion, the properties that we talk about. Okay. Similar to MGF, in multivariate case also, like you can define the MGF of this random vector x to be this quantity as a simple extension of that idea, and from where you can obtain this moments as evaluating by this, and x and y are independent if the the MGF of x y is given as product of the MGFs of the individual random variable as you. Okay. Now, apart from marginals, we also have the notion of conditional distribution, which is very important in any probabilistic study, right. So, you have what we have scenario, you have a PMF and suppose the marginal PMF of y is also exists, right. Then the conditional PMF of f given this is given by this ratio provided at this point y at which you are conditioning this is greater than 0. And the conditional distribution, you can write it in this form, which is you can write it in this form using this. Okay. In a similar way, continuous, but there is slightly different slight complexity with the, you can write it down, that the conditional distribution function you can define it because in a continuous random variable case, random variable taking a particular value is always probability is 0. So, this conditioning event cannot be equal to 0. So, what you do is that you take it in a small interval around that and then take its limit. That is how you define the conditional distribution function, and you have this quantity as the conditional density function is if this is related to capital F in this manner. Okay. Now, we know that whenever you have the joint PDF and this is the marginal PDF, at the points at which this marginal PDF of y is strictly greater than 0, the conditional PDF of x given y is equal to y exists and is given by the ratio of this, which is something similar to what you would have seen here, right. So, that is a way in normal cases, but this is the general definition, but this is the normal case with which we might work here. Okay. Now, connected with this is what we call conditional expectation, right. So, which is essentially like if I have the conditional distribution of x given y, I am looking at the conditional expectation of h of x given y is equal to y is defined to be this much similar to the other cases that we have seen. Similarly, conditional expectation of h of x given is defined for all values in this particular case for the continuous case, but in all these cases we are assuming that these expectations do exist. So, it is essentially in simpler sense for a fixed value of y, this would mean that the mean of the conditional distribution or the expectation of the conditional distribution. Now, if this is the case, that is what it is, right. This is what it would mean g of y. Now, if I replace this small y by y, that is how you define this to be this, then this becomes a random variable which has these properties, right. Note here, this property is what is relevant here for us, meaning that if you want to compute expectation of x, you can compute it in this manner. That is what it would, the implication of this is very relevant for us, that you can compute it in this using this condition. Okay. And then this tells you that this is the best estimate that you could have, which is not the case here. And similarly, for the conditional variance, right. So, variance of x y, suppose if you call this as this, where h of y is in this manner, which is basically the variance of the conditional distribution in some sense, then this quantity is what is we will be using it to compute variance of x by conditioning on another random variable y, but then you have to use this relationship to get this. Okay. Similarly, the conditioning argument also helps us to compute the probabilities of any particular event. So, this is what it is in terms of random variable that you are conditioning. Exactly same as the total probability law that we have seen earlier, provided if you assume this to be an event, this to be an event, finish, right. So, this is how you will get in discrete and in continuous, as you know. So, this kind of argument is what is would be relevant in our course, right. Now, again you can talk about conditional expectation of a random vector given a particular event, like this is again a event, but this is some generic event that we can take. Sometimes we may have to do this kind of computations that you have. Okay. You may also recall some other special expectation like characteristic function. As I said, this is essentially expectation of e to the power I t x. Okay. Modes of convergence, there are 4 modes, right. One is called weakly, almost surely, and rth mean and improbability. Like these are the 4 types of convergence and limit theorems, like this law of large numbers and the central limit theorem, which are the most important results, and their significance and so on. And also some of the inequalities like moment inequalities, means Chebyshев Markov inequality, which sometimes you may have to use, and functions of random vectors, especially sums of random variable, how one can handle the sums of random variable in case of multiple number of random variables that you have to have, right, and computational expectation by conditioning again, and handling of random sum of random variables, etc., etc. Like some of these concepts, if you are familiar with, it will be very useful if you can understand easily. So, what we have seen is basically the notations mainly that we want to introduce, that we might use in our course further, and you can get familiarized with this, and you can also recall the basic concepts that we have seen, that you have studied in your probability theory, so that you can get on with the course very nicely. And I have introduced the notations and the basic concepts and what you need to remember here. And here what we have is a table which gives us a sort of a ready reference for us, that certain probability functions, parameters, and the mean and variance, and their MGF and their PGF. As you know, MGF and PGF are written by this. So, if I replace e to the power t by z, I am going to get the PGF in case of when the PGF we can talk about, which is a case only if you have non-negative integer value random variable. So, all these random variables have support in this. Okay. The support part we did not write here, but that is understood. Like for example, in this case, binomial case, what are the support that you have here, right? Your x ranges from 0 to n, right? This is set of all non-negative integers like geometric, this form, and this is negative binomial, right, and the relationship between the different distributions. So, for each of these distribution, if you can concentrate here a little bit more, binomial, like this MGF PGF will be relevant for us whenever we want to identify something that we have derived is of this form. Oh, then we say that okay, this is of this form, so that means this must be corresponding to a binomial distribution, right, because the PGF or MGF have an one-to-one relationship with the corresponding distribution. So, either you talk in terms of the probability distribution or in terms of their MGF or PGF, the results are going to be one and the same. So, mainly for us, for example, like these two distributions, Poisson and geometric, are very, very important apart from others. Of course, negative binomial as well, because that is occurring as a sum of, you can think about the other one, binomial is sum of Bernoulli and so on, right. So, these two distribution, of course, for example, then these quantities, like you would see that very frequently occurring in our calculation that we might do. Okay. And this is one form of geometric distribution. As you know, there is another form of geometric distribution also, which is written in this form. The difference being this x minus 1 here and x here, one denotes the number of trials required to get the first success, and the other one is number of failures before the first success, right, if you have to distinguish between these two distributions. So, both these forms might be useful depending upon the scenario that you might encounter here. So, this is all some of the discrete distributions and their moment generating functions. Similarly, we would also like to focus on a bit more on this continuous time distributions and moments and MGFs as well. So, here especially as usual, like in the discrete case, so here we might more use these kind of distributions than normal and uniform. So, the exponential distribution, Poisson distribution, these are bread and butter for all this, many of the initial phase models that we might go into consider. So, this is again in that sense this exponential distribution of this form, okay, and this is its MGF. Okay. So, the characteristic function, if you want for either discrete or continuous, you can always look at replace this t by it, then you are going to get the corresponding characteristic function. Okay. So, gamma, which one can think of as sum of exponential, IID exponential, like this alpha number of times. So, here alpha in general could be any number, but suppose if alpha is an integer, right, alpha is an integer, then that is actually then you can think of sum of n IID exponential with the same parameter theta. See, Erlang distribution is what we might call a special case of gamma in some sense. If you have to see, suppose if I look at here, what we have done is that this theta we are replaced by theta k in a way. The reason is suppose 1 by theta here also 1 by theta, whereas here something else will come. So, we want to do some adjustments here, right, but where here k is restricted to 1, 2 and so on, right. So, this is basically you will understand as you go to the theory, this is what we would actually mean the sum of exponential, but the parameters are tweaked a bit in a way, the sum for the exponential. And two term hyper exponential, this is what you call it as a mixtures of two exponential, like this is what it is scenario here. So, essentially here exponential, if it is in some sense, if it is put it in series, then you will get is Erlang k, and if it is in parallel, you will get this hyper exponential and so on. Okay, again a general version of this is what is hypo exponential, which will also be used. And sometimes a gamma distribution with a certain parameters, right, n by 2, where n is this set of natural numbers and theta is half, is known as the chi-square distribution, which will arise in our studies in this case. Okay. So, these are some of the distribution that we might encounter. Okay. So, what we have done so far is that we have basically reviewed the probability theory, like whatever you know, this is nothing new for you, because we are assuming this knowledge of probability theory. What I have highlighted is what are the quantities of interest that are most relevant to us, and what are the notation that we might use when we go further. Okay. So, this is a quick review. So, like we just cover it up in this video, this complete portion, that what you might go through, what you might recall, and what you need to little bit more elaborately you need to look at. Okay. Fine. So, with this we will end this review, and thank you. Bye.